in the last lecture, we started talking about the implementation of the factorization algorithm due to Shor. We will continue with our discussion and see how exactly a quantum computer will be able to implement it. But let me summarize what we did so far. We said that suppose I have a number n which is equal to a product of two large prime numbers. Even though in principle my algorithm is applicable to large prime numbers, my illustration in this, for the purpose of this course, will be for relatively simple numbers, because that will only enable you to appreciate what we are actually doing. Now, we have seen that there are algorithms like Euclid algorithm or even better algorithms which can compute P and Q, but they are not fast enough. The traditional Euclid algorithm takes square root of n steps in executing this. The fastest possible algorithm that is known today using a traditional computer is has a complexity which is exponential of logarithm n to the power 1/3 and log n to the power 2/3, which is still fairly slow. So the problem that we stated was the following, that we need to solve an auxiliary problem, and this auxiliary or equivalent problem is finding or having an oracle which can compute what we call as period of a function. So what we do is this: we choose a random value m which is less than the n which we are required to factorize, such that m is co-prime with n. We already had defined what is meant by a co-prime, that is m and n do not have a common factor. Having done that, we defined a function f which goes from the space n to n, and the function is equal to m to the power a modulus of n, where a is some number. The smallest value of p belonging to n, for which m to the power p modulus of n is equal to 1, that is the value of a for which the fn of a becomes equal to 1. That is called the period of the function. The quantum computers can do this step very effectively. Now let's see how this does it. So we take an arbitrary value of m, compute its various powers till we find m to the power p is equal to 1 mod n. Now if p happens to be odd, the algorithm will fail, because as we have seen in our last lecture, that this algorithm is based on the fact that if I have an equation x square equal to 1 mod n, then if n is a prime number, then I will have only the trivial solution, which means x is equal to plus or minus 1. But if n is a composite number, then we have seen that it will have non-trivial solutions. But the original equation based on which it was done was x square equal to 1. So therefore, if I have an equation of the type x to the power an even number equal to 1, then only my algorithm will be successful. If n is large, the classical computer may require evaluation of the order of n powers of n. In a quantum computer, as we have seen, all the powers of m will be simultaneously calculated and stored. Of course, we have been pointing out time and again that in order to extract p, I need to go through certain exercise, because if I simply do a measurement after the oracle has evaluated it, I would simply get a value of the power with an arbitrary probability. Now suppose p is even, so that we can use this algorithm, then we factorize that m to the power p minus 1 equal to 0 to m to the power p by 2 plus 1 into m to the power p by 2 minus 1 equal to 0. M to the power p by 2 minus 1 equal to 0 is not a possible solution of this equation, because we have seen that p is the smallest integer for which m to the power p is equal to 1. Since p by 2 is smaller than p, this is not possible. That leaves us with m to the power p by 2 plus 1 equal to 0 mod n. If that happens again, the algorithm fails. The algorithm becomes useful if m to the power p by 2 plus 1 is not equal to 0 mod n. Now if this condition is also satisfied, then the solution of this equation, m to the power p by 2 plus 1 into m to the power p by 2 minus 1 equal to 0 mod n, will have the relevant factors of n in it. And this is basically the algorithm. Now the question is, how do you execute this? The first step is to choose the size of the register. What we do is, we take an L qubit register, and L is chosen such that 2 to the power L lies between n square and 2n square. Some books would suggest that you take even a wider berth, that is, choose L such that 2 to the power L lies between 2n square and 3n square, but that's a matter of choice. Let's call Q equal to 2 to the power L. The reason why we will choose Q to be a power of 2 is because it will enable us to perform quantum Fourier transform process smoothly. The first task is to initialize. I take two registers of this size that I have mentioned, and I first initialize both of those registers to the null state. Having done that, I apply a quantum Fourier transform on the first register. This is something which you have been doing time and again, because since these are simply null state, the process is nothing other than passing all the 0 qubit states through Hadamard gates, and then we will get a uniform linear combination of the basis states. So therefore, at this stage, my state of the system, which I will call as psi 1, is given by 1 over square root of q, x equal to 0 to q1, state x, and of course the second register is still in state 0. I will now choose a random number m, which, as we have seen, must be co-prime with capital N, and then I will have a quantum oracle to compute the various powers of this m modulus n, and I would like to store these in the second register. So this is clean and it does not require much of an effort. Now let me illustrate this with an example. I will take number n to be 55. Now you would say that you are using a quantum computer to factorize such a small number. As I have told you time and again, I would like the principle to be illustrated by small numbers which I can execute on the desktop. Now if n is equal to 55, which of course I know have factors 11 and 5, let me choose m. Now in principle I could choose m anything other than a number which has either 5 or 11 as a factor. But let me just randomly choose a number 13. So my job now will be to calculate various powers of 13. So 13 to the power n. Now this I have shown it on my slide, various powers, but let me try to work it out on the paper as well. So the thing is this, that you can see 13 to the power 1 is of course 13. Remember, these are discrete arithmetic. Now because of the discrete arithmetic, we have certain advantages which I should use. Now 13 square is 169, which is nothing but 4 plus 165. 165 is nothing but 3 into 55. So this is equal to 4. I will not write it always, but let me remind you, this is mod 55. How do I calculate 13 cube? Do I calculate 13 cube and proceed? The answer is no, because 13 cube is nothing but 13 square into 13 to the power 1. So it is 4 into 13 equal to 52. This is the attractive thing about modular arithmetic. What about 13 to the power 4? 13 square is 4. So therefore 13 to the power 4 is 4 into 4 equal to 16. Like this, you can carry on the various numbers. So let me just repeat a few of them. 13 to the power 5 is 43. You can try out various results. 13 to the power 15 happens to be 32. And finally, as you go along, you will find 13 to the power 20 happens to be equal to 1. Now, this is not very difficult to work out, because we have seen this is what actually we would do in order to compute these numbers. So therefore, period of m equal to 30 is 20. So most of my effort today will be to use this example and carry you through the general process that I have introduced. Now, we have said that we must choose the size of the register to be an L qubit register which lies between 2n square, n square and 2n square. A simple calculator will tell you that n square is 3025 and 2n square is 6050. 6050. So I can find out what is the L value which satisfies this inequality. And you can then see that the possibility is Q equal to 2 to the power 12 equal to 4096. So therefore, I take a 12 qubit register. At that stage, my value of psi 1 then, which we have seen is obtained by passing the null state of the first register through Hadamard gate, and this is then 1 over square root of 4096, which just happens to be 64, 00 plus 10. Remember, the second register continues to be in the 0 state. Last one will be 4095, 0. Now, what do I do for the second stop? In the next case, I compute the various powers of m, which has been chosen to be equal to 13, and then store my result in the second register. The second register had 0, so the oracle will automatically give me the value of the function itself. And at that stage, I don't disturb the first register at all. So psi 2 will then be square root of 4096. This is 0. Now I need 13 to the power 0, which is equal to 1. Then 1 and 13 to the power 1. So that's nothing but 13. I have actually made that table, so it should not be very difficult to work out. But on the other hand, let's write one or two terms. So 2 13 square. 13 square, as we have seen, is 169, which is equal to 5 mod 55. Sorry, this is 4 mod 55. And like this I can go till I reach 20. Then I say the second register is 13 to the power 20, which we have seen equal to 1 mod 55. And then my entire series from here starts again. And finally, I will get to the last state, which is 4095, comma 13 to the power 4095. And this will work out to, I think, 31, but you can check it. Now at this stage, suppose I were to measure the second register, then what I would get would be a random value from 1 to the last value that I calculated for 13, various powers. And let me go back to my table there. You can see these were my various values, and so if I measure the second register, I would get 13, 4, 52, 16 like this. And a measurement of the second register and throw in any result, and you can use any one of the members on this table to do your calculation. But let me say measuring second register gave me supposing it gives me 9. Now if it gives you 9, refer back to the slide again, you find that I have here 13 to the power 6 equal to 9. So I will, if I have measured 9, then at that time my first register might have been in any states like 6, 26, another 20, 46, etc., etc., etc. So the result that I get is the following: psi 3. Since I have made the measurement of the second register, I have to actually count how many times 9 appears there. Now this is not too difficult. See, what we have are 4096 states there, starting from 0 to 4095. Now in that case, I get the 6th one, the 26th one. So since I know the period to be 20, I can immediately count that there are total 204 states in the first period, because once I have a 6 there in the first period, I will have a 26 in the second period, 46 in the third period, etc., etc. But then 204 into 20 is 4080. So remaining 16 of them, where 9 comes, also will appear once more. So in other words, I will have 205 values of in first register. Corresponding to the second register having a value 9. And once I have normalized that state, I will have psi 3 equal to 1 over square root of 205, 6, 9, 26, 9, etc. And you can check, it should be equal to 4080 was the end of a period. So therefore, last one would be 4086, 9. In general, structure of this would be given by what is shown in the slide as 1 over square root of m. M is the number corresponding to this number, which is the number of states in the first register corresponding to a given value in the second register. And this is the combined state. Supposing my measurement in the second register is k, then the first register will have x0, which is the starting point, plus the position in the period. Is it in the first period, which you may call 0, d equal to 0, second period, third period, etc. So d is a running index on that, times period. So this is exactly what is written down here. Now at that stage, we will apply QFT on the first register. This requires a bit of an algebra, but let's look at what am I getting. So we had, in principle, psi 3, let me write it down, equal to 1 over square root of m, sum over d equal to 0 to m minus 1, which is just the running index of which period it's in. X0 is the starting point of that first register, for which the value in the second register was k, plus d times p comma k, which is the result of the second register, which in my example I told you as 9. Now if I now introduce a QFT on the first register, I will get psi 4. So now QFT is being done on the first register, which has q number of elements. So therefore, this is square root of q times m, sum over y equal to 0 to q minus 1, sum over d equal to 0 to m minus 1, exponential of 2 pi I y into x0 plus dp by q and y k. This is standard definition of the Fourier transform. Now let us write it in a particular way. So this is equal to 1 over square root of q times m, sum over y equal to 0 to q minus 1, e to the power 2 pi I y x0, the first term, by q, multiplied with sum over d, because d is only appearing in the second term, e to the power 2 pi I y dp by q, and then of course yk. Now let me write it, this sum over d, you notice that this is only there in this term. So this is equal to 1 over square root of qm, sum over y equal to 0 to q minus 1, e to the power 2 pi I y x0 by q, sum over d, we put it in bracket, let's call this z to the power d, and of course yk, where we have defined z to be given by e to the power 2 pi I y p by q. let us look at what this quantity gives me, because once I have this now, supposing I were to measure the first register. Now, if I am to measure the first register, what will I get? I will get a particular value of y I will get a particular value of y with a probability 1 over qm, because there was a 1 over square root of qm there, and this term is a unimodular term, so that is 1. So I am left with modulus of sum over d equal to 0 to m minus 1 z to the power d whole square. I have written down what is this z here, and this d, the sum over d is a finite sum. Since the sum is a finite sum, I will be able to execute this sum and find out its value, and this will give me the probability with which a particular state y appears. We will see in the next lecture that this probability has peaks at particular value of y, which enables us to determine the period p. And so therefore, by repeated measurements and certain smart manipulation of the result of such measurement, we will be in a position to find the period. And this, as we have seen, is what was our biggest challenge in solving the problem of factorization. So in the next lecture, I will compute this value and illustrate it for the example that I have given, that is for n is equal to 55, and then tell you what is a fast method of computing the value of the period from the result of the measurement of the first register.